All right, let's talk about heat transfer, energy transfer by heat. So heat is a form of energy that can be transferred between systems, and it depends on a temperature difference. So it can cross system boundaries, right? If you have a closed system, your energy can cross as heat or work, right? And we already saw. Well, we'll talk about work in a little bit, but we're going to talk about heat. Heat is this energy crossing due to temperature. And oh, I've got to just realize I have to click my mouse a certain way to get the laser pointer. Temperature difference is the driving force, right? So here we have air temperature of 25 degrees C. This soda is already at room temperature. It's been sitting out. It wasn't in the fridge. So there's no heat transfer. In the second soda, you can see this is 15 degrees C. So maybe you just pulled it out of I don't know, a cooler. And there's heat transfer from the room to the soda at 8 joules per second. Now the temperature difference actually affects the rate of heat transfer. So you can see here we have a soda at 5 degrees C. And instantaneous rate of energy transfer is 16 joules per second because it's a larger difference in temperature between the room and the soda temperature. So again, we're looking at energy as heat transfer if it crosses the system boundary. So internally here, this is the baked potato, right? We're not looking at internal differences in temperature. We're considering this our system. So you take a baked potato out of the oven, and it just sits there. It's got a certain amount of thermal energy, right? And the heat is as it's crossing this boundary, 2 kilojoules. That's how much heat it's losing. And it's dumping that to the environment, and the environment is increasing by 2 kilojoules of thermal energy. Okay, here we have heat transfer per unit mass. Again, you can divide Q is total energy, right? Kilojoules, that's the heat. Divided by mass, you get a little q, that's kilojoules per kilogram. That's your heat transfer per unit mass. You see down here that q is actually just an integral over time of the rate of heat transfer. Now, this is because, as I mentioned earlier, right, the difference in temperature determines the rate of heat transfer. So a soda might start off at 5 degrees C in a room of 20 degrees, and at the initial time, it's got a certain rate of heat transfer, right? As the temperature difference closes, as it gets smaller, this rate of heat transfer is going to drop. So you see that the Q is an integral over time, right? Because Q dot may be dependent on time. Well, it's definitely dependent on temperature, and temperature is dependent on time. So when heat transfer is constant, you can just pull this out of the integral. It's just Q dt, well, Q dot dt. And here's a relationship between little q, big Q, and Q dot, which I don't know what happened to the dot on this slide. But for example, in here, you have 30 kilojoules of heat crossing the boundary, right? So 30 kilojoules crosses the boundary in 5 seconds, and you have a certain mass of 2 kilograms. That gives us a Q dot, a rate of heat transfer of 6 kilowatts, right? That's 6 kilojoules per second, 30 divided by 5. And then we divide kilojoules per, well, the 30 kilojoules by mass, we get 15 kilojoules per kilogram. That's little q, right? So we take big Q. To find little q, we divide it by the mass. That's 15 kilojoules per kilogram. To get Q dot, we divide it by the time. That's 6 kilowatts, or kilojoules per second. All right, energy transfer by heat. Know what an adiabatic process is. Adiabatic means there's no heat transfer between the system and its surroundings. Typically, you'll see something like this. You'll see some insulation around it. a lot of problems start with an adiabatic system is brought from state 1 to state 2. So adiabatic means either the system is well insulated or the system and the surroundings are at the same temperature, so there's no driving force for temperature. And typically we're going to use adiabatic in the context of well insulated. But if you're doing an analysis and there's no indication of temperature difference between the surroundings and the system, you could also in some cases assume it's an adiabatic system. This is just historical background. They used to think that, so the word calorie comes from this caloric theory. They used to think that the heat transfer was actually some kind of substance called caloric that didn't have any mass or color or taste, and it was moved from one body to the other. Now we have like kinetic theory, and we understand that, well, kinetic theory treats molecules as just tiny little balls that are in motion, right? And now we understand heat is basically this energy associated with random motion of atoms and molecules. Finally, we typically talk about 3 mechanisms of heat transfer. We have conduction, which is when you put 2 objects in direct contact with each other. So that way their atoms can actually, atoms at the surface of one can transfer energy to atoms at the surface of the other. We have convection. Convection is heat transfer typically inside of a fluid. Probably one of the most common, one thing you can do to feel convection, right, is go stand next to a window on a very cold day, right? And you can feel that just standing further away, you can maybe get a convection current going. Or you look at a flame, right? The air around it, if you see the smoke rising, right? That's convection. But this is combined effects of conduction and fluid motion, right? So you have a hot fluid rising, and maybe it's interacting with a surface and transferring heat that way. Finally, we have radiation, and this is just transmission of energy from electromagnetic waves. So like, the sun is transferring energy to the Earth via radiation.